All right, guys, hi again. Now, you may have the feeling that I'm going a bit fast. As I told you, the theoretical parts we are going to have on online classes, okay? And during our physical class time, I'm just going to show a few problems. And we do not have much time. We have only 2 weeks left, not including this week. And next week, we are going to have quiz in our physical class time. And after the 2 hours of online class, and that's it. That's why we have to cover all everything order from chapter 1 to chapter 6. So you have to do a lot of self-study. And next week also, I'm thinking to have some problem solving session. Okay, I will see. I'm not sure if I can find some your free time or not. So now we're going to talk about the fundamental theorem of calculus. As I have told you, actually, that one is the most important. What is it? The theorem of calculus. That's why you say it's a fundamental theorem of calculus. And what is this about? Actually, it is about the connection between the differentiation and the definite integral. So in this section, we present the fundamental theorem of calculus, which is the central theorem of integral calculus. It connects integration and differentiation, enabling us to compute integrals by using an antiderivative of the integrand function rather than by taking limits of Riemann sums as we did in section 5.3. And once again, guys, look, to understand this thing, how useful it is and what is the power of knowledge, okay? And you need to practice a few questions in 5.1, 5.2, and even 5.3. And you need to have this kind of feeling that, okay, calculating definite integrals using the Riemann sum and the limit of the Riemann sum, it is very, very tedious job. You know, it's really, really long. Even just calculating the area under the curve f of x equals x squared over the interval AB, right? It's quite long. It's just very simple one. How about if it is x cubed? How about if it is x to the power of 5? It's very, very long. And that's why just discovering this new thing, right? The knowledge, right? This knowledge. Now we have a key to open the door. You don't have to break the door, or you don't have to break the wall, right? And just turn the key and you can enter the house. It is something like this. And that's why mathematicians say that actually discovering this fundamental theorem of calculus, or after proving this one, actually it fueled the development of science or math. Okay. All right. So now we are going to start with the mean value theorem for definite integral. That we are going to use this, okay, to prove our fundamental theorem. It says that if f is continuous on AB, then at some point C in AB, f of C is equal to 1 over b minus a times definite integral of a b f of x dx. Now, what is the geometric meaning of this one? Once again, look, as I said, ignore this blue line, right? It's a graph of the function. Suppose that we have a kind of container, the glass container, right? Let's say in 2D, okay? Now, if actually the water, right, gets back to its initial states, right, in the container, the top will be horizontal. It will be parallel to the ground because of the gravitational force, right? So we are saying that if it is so, then the average height, right, this f of c, always, actually, we can find that, you know, this f of c over the interval, we have f of b, and always the area of the rectangle whose height is the average value of the function will be equal to the area of the region which is bounded by which is under this curve. And what is the proof of the mathematical proof of this one? Again, we are going to use the last inequality property in definite integrals. So that is, if you remember, what was it about? Proof. So for every function, right, we can write this inequality. Here we have maximum, not maximum first, I need to write minimum. So minimum value of f times over the interval a b, right, b minus a, is always less than or equal to integral from a to b, f of x dx less than or equal to maximum value of f times b minus a, right? Now, if you divide all sides by b minus a, because I know that b minus a is positive number, right? What do we have here? Here we have minimum value of f less than or equal to 1 over b minus a, integral from a to b, and the f of x dx less than or equal to, and here we have maximum value of f, right? And since our function is continuous, right? It says f is continuous over the closed interval ab. So that means that by the first actual theorem about the continuity, our function assumes all the values between this minimum value of f and maximum value of f, right? If you look at this graph, actually, this one is the minimum value of f. Let me just label this by lowercase m. And how about this value? This value is maximum value of f, right? Let me label this by capital M. So it must take all the values between these 2 points, right? It must take all the values between these 2 points because it is continuous over the interval AB. And particularly, I can find some C, right, over the interval AB, right, where this f of C is equal to the value of this integral. Example, show that if f is continuous on the closed interval AB and a is not equal to b, and if this definite integral, right, a to b f of x dx is equal to 0, then f of x equals 0 at least once in AB. Okay, show that if f is continuous on AB and a is not equal to b, and if this definite integral is equal to 0, then f of x is equal to 0 at least once in AB. Now, how to show this? Show this that means that we have to prove with that f of x can be 0 at least at once in AB, right? By using the mean, the average mean, the mean value theorem, right, for definite integral, we have at least one c in the interval AB, where this f of c is equal to 1 over b minus a times integral from a to b, and here we have f of x dx, right? And this definite integral is given is equal to 0, and that's why the thing is equal to 0. So which means that there's at least once in the interval where the value of the function is equal to 0. Okay, guys, now immediately let's just focus on this, the fundamental theorem of calculus part 1. I'm actually saying again and again and again, this one is, if you can prove yourself one more time, it will be great for you to understand this calculus. It will be a life lesson for you because it really, I would say, changes the way you look at things in calculus class. Now, the fundamental theorem of calculus, part 1. It says that if f is continuous on the closed interval AB, then this capital F of x is equal to the definite integral from a to x f of t dt. Is continuous on AB and differentiable on AB, and its derivative is f of x. Okay, so the theorem is saying that if you are given a function, continuous function over the closed interval AB, right? It's saying 2 things. What is it? It's saying that number 1, it is differentiable, right? It's differentiable, and we are just labeling this definite integral by f of x, right? This capital F of x is differentiable, and its derivative is equal to the derivative of this definite integral. What should you understand from here? From here, you should understand that if you are given a function f of x, right? If you integrate and differentiate, you will get back our original function here. Or this is the same thing. Here, if you differentiate or if you integrate, and after the differentiate, you will get the original function. Or if you differentiate and integrate, you will get again the original function back. Okay. And that's what we are going to prove here. Okay, why this f prime of x is equal to f of x if f of capital F of x is equal to this definite integral. In our second part, in the fundamental theorem of calculus, the part 2, we will learn how to evaluate this. Okay, we'll see that this f actually is just one of the antiderivatives of the function f. Okay. Now to do this one, guys, we are going to use again the definition of our definite integral. And suppose that we are given the function and it is graphed over the interval AB. Okay, interval AB. Let's say this A and B. Suppose it is something like this. Okay, it can be anything, it doesn't matter. Usually we just draw like this. And this point is A, and this point is, let's say it is B. Now we know that what is this area under this curve is just a definite integral, right? It's a definite integral because fixed, right? It's definite integral. Now what are we going to do here is, how about if I just choose a point and suppose that, and this one is, it is, let's say it is X, okay? Now how can I find the area of this one? Okay, the area of this part, this red shaded region or under this curve, it depends on the value of X, right? So at the time, actually the area of this one, it depends on the value of X, it will be f of X. Then what is f of X? This capital F of X will be equal to integral from A to X, and here we have F. I have already used X. That's why I cannot use here because you may get confused. So that's why we are just using T and dt. All right. So because also it means f of x dx, but usually this x and x, they're different things, right? This one is variable, one is the upper integration limit. And a lot of times I feel that students, they don't actually or they get confused when I use different variable here inside this integral. So that one is f of x is equal to this. Okay, so what am I going to show here is if you differentiate this f of x, I'm going to get this f of this lowercase f, right? So by definition, what is the derivative of this f prime of x? This f prime of x by definition, that's equal to limit as h approaches 0, and here we have f of x plus h minus capital F of x over, and here we have h, right? So now, if you look at this expression, the numerator, f of x plus h minus f of x, what is it? It's the difference between these two areas, right? This one is f of x, and let me just label this one by, what is this? X plus h. Actually, that area, right? What is this area? And this area, let me just write here, this area is f of x plus h, right? And removing this f of x part, right? Is minus f of x. Okay, so f of x. All right, so that's equal to this. So that means that now I can just rewrite this as limit, and here we have h approach 0, and here we have 1 over h times, let me just write like without brackets. So here we have 1 over h times, what is f of x plus h? By definition, that's just integral from a to x plus h, right? X plus h, and here we have f of x dx minus, how about this f of x? That is integral from a to x, right? That is f of x and the dx. Okay. So again, actually the properties of the definite integral, right? And this one, actually this integral, I can write it as that's equal to integral from a to x and f of x dx plus integral from x to x plus h, right? And here we have f of x dx. As here at the time, these two things, they cancel each other, right? So then this limit is equal to, we just write here, this limit will be equal to limit as h approaches 0. So here we have 1 over h times, and this a to x and a to x, they cancel each other. What do we have here? Here we have integral from x to x plus h. And here we have f of x and dx, right? It is f of x dx. Again, I have x here, right? That's why I have to use something different here. Because if I use the same thing, it will be confusing here. So here we have f of t and dt, and f of t, and here we have dt. Okay, and also here I need to use f of t and dt. Okay, so now I am going to use the mean value theorem for definite integral. If you look at this part, okay, let me just rewrite this thing again here. What we have here on the left hand side, right? I have f prime of x. On the right hand side now, I have this limit as h approaches 0, and here we have 1 over h times integral from x to x plus h and the f of t and dt. Okay, so now if you look at this using mean value theorem, right? So we are just talking about this one part here. Maybe it's something like this. Okay, so this one is x, and this one is x plus h, right? So this mean value theorem says that's actually what is the length of this part that is equal to, what is it? That one is equal to, it is h, right? And this mean value theorem says that then there exists some c right here on this actual somewhere here we have c, where that's equal to 1 over x plus h minus x, that's equal to h, an integral from x to x plus h. And here we have f of x dx, right? And again, actually, to right here, f of t and dt. Okay, so I can replace this by this integral. Look, limit. I'm going to write a bit later. And the thing we have some c, right? I can write c here, where c belongs to the interval. Here we have x and x plus h. Now, what happens here when actually h gets smaller, right? It gets to 0. You see here, and also c approaches x as h approaches 0. Because if this interval gets thin, I mean shorter and shorter and shorter, that means that also we are pushing back the c towards x, right? And that's why if h goes to 0, and also c must be approaching x. So now instead of this h, now I can replace it by the c is approaching x. So that thing is equal to f is a continuous function, right? And using the definition of the continuity here, when c approaches x here, then just this thing is equal to f of x. As here, what we start our actually expression here, we started with f prime of x. Now on the right hand side, we have our original function. Okay, that means that if you integrate the function and differentiate this, you can get our original function back. Or if you differentiate and integrate the function, again, you can get the original function back. That is very, very powerful and useful theorem in, what is it? Integral. Without this one, it is, I mean, it will be really, really tedious and difficult to calculate the definite integrals. Let's say immediately they use the fundamental theorem to find dy dx if y is equal to this, okay, a to x t cubed minus 2t squared, okay? By using fundamental theorem, right, of calculus. And what is dy dx? dy dx, and here we have, what is it? D dx of what? Our function that is from a to x, and here we have t cubed minus 2t dt. And what is our function here? Is our function is t cubed minus 2t, right? So this definite integral by the fundamental theorem is equal to t, not t, actually, this must be an x, right? So that's equal to x cubed minus 2x. And how about from x to 7, right? First, I have to change this using the property. I can rewrite this as minus integral from 7 to x, because this lower integration, what is the limit? It must be a constant number, right? So here we have 2t times cosine of t, and here we have dt, right? So from a to x, right? And here we have a function. So by fundamental theorem, right, that's equal to minus 2 times x times cosine of x. use the fundamental theorem to find dy dx. Now, actually, we do not have x, but here we have x squared, right? At that time, how should we calculate this? To do this one, actually, this x, actually, of course, this x and this one, it must be the same. But to do this one, we are going to use substitution here. And suppose that here we have u is equal to x squared. Okay, so then here we can write here what is du. Du is equal to 2x dx, right? So that means that I can change this dt with what is it, dt, right, with du over 2x. Right? So at the time here we will have, maybe I need to write here, okay, continue. So then dy dx will be equal to, here we have d and dx integral from 2 to x squared. And here we have sine of t and dt. Okay. All right. So that's equal to, just a second. All right. Okay. So now, if we have here, we have u here. What do we have here? At the time, we need to have here sine of u, right? But if it is sine of u here, so let me just write here dx and I change this into du. Dx. All right. Look, this x, everything that we change into u. So here we have d, right? And from here, what is dx? Dx is equal to du over 2x, right? So here we have du, and I have here 2x. So integral from a to u. And here we have sine of t, or even I can write x here, and dt, right? So that's equal to 2x. Now, if it is u here, we can have what is the sine of u, right? So that is sine of u. What is u? Sine of u is equal to x squared. I think it may be a bit confusing, but you have to think again, okay? Because see here dx, right? If I introduce this u as x squared, and what is the differential of du? I mean, u, that's du, that's equal to dx, 2x dx, right? Now I have to change this dx, right, by what is it, du over 2x. So here we have 2x, it has nothing to do with this. Now here we have u, because to use the fundamental theorem of calculus, right? And at the top, right, is the upper limit, integration upper limit, right? And we need to have just a single variable, this x or y or something. Now again, let's see another thing here. How about this one? So we need to find, what is it, dy dx, right? So that is d dx. So we have to differentiate this 1 to sine of x, and here we have 3t squared and dt. And also here in this case, what I'm going to do here is, okay, suppose that u is equal to sine of x, right? From here, then what is the differential of the u? That is cosine of x, and here we have the x, right? We practice how to find the differential. So as say here, this dx, right? From here, dx can be replaced by du over cosine of x. So now if I just substitute here, what we have here? Here we have d, right? And here we have dx. What is dx? Du over cosine of x. So I need to write cosine of x at the top. So here we have cosine of x d, and okay, here we have du and cosine of x, and here we have d, and integral from 1 to u and 3t squared dt, right? So what do we have here now? Here we have cosine of x, and from 1 to u, right? Actually, it must be x again, this whatever it is. So here we have 3u squared, right? 3u squared. So that is 3 times u squared. What is u? U is equal to sine. So here we have sine squared of x. Why did I write 3 here? We have 3 here, right? Because of this. Okay. So that's equal to 3 times cosine of x. And here we have sine squared of x. So that means that if you integrate now this function, you will get our f again. Now, actually, the second thing is, what is it? Fundamental theorem of calculus part 2. Okay. So the part 2, it shows us how to evaluate this definite integral. It says that if f is continuous at every point in AB, in closed interval AB, and f is any antiderivative of f on AB, then this definite integral is equal to f of b minus f of a. That means that just you need to find one antiderivative of f and evaluate its values at b and a, and subtract, okay? It gives us the value of this definite integral. Why is this so? A solution, let's say this proof, right? Now suppose that, okay, this g of x, okay, is equal to integral from a to x, and here we have f of t and dt. Okay, so because in fundamental theorem part 1, it says that if f is continuous at every point in AB, then this f is differentiable, right? And actually this differentiable means that this integral is equal to the g of x. And suppose that this f is any antiderivative of this function f. So that means that here, suppose that this f prime of x is equal to f of x. And also from here, we know that actually g prime of x, right? If we differentiate this, that's equal to f of x. Now, if you remember the corollary, then the difference between these two guys, right, f and g, it must be a constant number. So that means that this f of f of x should be equal to g of x plus c, right? So now if you evaluate this, what is f of a? F of a is equal to g of a plus c. And how about f of b? F of b is equal to g of b plus c. Okay, so now if you subtract this, what do we have here? Capital F of b minus capital F of a, that's equal to, it's just g of b minus g of c, right? Sorry, g of a. And what is g of b? G of b is equal to integral from a to b, and here we have f of x dx, right? And the minus, how about g of a? It's integral from a to a, f of x, and the dx. And this from a to a, we know that that's equal to 0. So on the right-hand side now, we have integral from a to b, f of x dx. Okay. So now, guys, we are ready to how to say compute the definite integral using this fundamental theorem of calculus. To calculate the definite integral, just we need to find one antiderivative of the function, right? And evaluate its values at b and a and subtract. Example, calculate the following definite integrals. And what is the antiderivative of this sine of x? That is minus cosine of x, right? One of them. So that is, then it is minus cosine of x. So just I need to evaluate this at point A and pi, right? So that's equal to minus. So here we have cosine of pi minus cosine of A. And what is cosine of pi? Cosine of pi is equal to -1, right? So that's equal to 1 plus cosine of A. And how about this square root of x plus 2 over x squared? And also we have studied this before, right? And what is the antiderivative of this function? Square root of x, that is x to the power of 3 over 2 over 3 over 2 plus and 2 times. How about x to the power of negative 2? It is x to the power of negative 2 plus 1 over negative 2 plus 1. And the integration limits, it is from 2 to 7. So that's equal to the first part, if it is 7. So here we have 2 over 3 times 7 to the power of 3 over 2. And this one is 2 plus 1, right? It is minus 1. It is negative 1. So here we have negative 2 times 7 to the power of, what is it? Minus 1. Minus, and here we have when it is 2, here it is 2 over 3 times 2 to the power of 2 over 3 times here, and minus 2 times 2 to the power of minus 1. And now we just simplify this and get the answer. And how about B? And oh, it's ACB. Okay, no problem. Now secant of x and tangent of x, right? So what function's derivative is secant of x tangent of x? If you remember, it is secant of x, right? Because if you differentiate secant of x, we get secant of x times the tangent of x. So here we have minus pi over 4 to 0. So that's equal to secant of 0 minus secant of minus pi over 4. And what is secant of 0? That is 1 over cosine of 0. That's equal to 1. And the cosine is an even function, so it is minus. What is secant of pi over 4? That is, what is it? Just square root of 2, right? Okay, 1, 2, 3, 4, 5. Okay, but anyway, we have to finish them today. The net change theorem. The net change in a function capital F over an interval from a to b is the integral of its rate of change. That is f of b minus f of a. That's the net change, right, in a function capital F, right? So that means that when we just say net change, if you're talking about, for example, let's say this one is capital F, this one is x, right? And let's say this one is a, and this one is b, right? When we just say that the net change, we mean actually this change, right? That is the net change, okay? Because this value is capital F of a, and this value is capital F of b. So this one is the net change. So that's the f of b minus f of a. So what is it? To find the net change, saying that here, just evaluate the definite integral of its rate of change, because it's f prime of x, it is the rate of change of this function over this interval, right? All right, use the net change theorem to evaluate this. Okay, to evaluate this one first, actually this x times cubic root of x plus fourth root of x dx, right? So what is this? Suppose that that's equal to f prime of x. So first, to evaluate this, how we need to find it is antiderivative, right? Let me just write here, it is capital A, the solution. Okay, solution. First, let me simplify this. This a, that change is equal to from 0 to 1. And here we have x to the power of 1 plus 1 over 3. So here we have 4 over 3 in power plus 1 plus 1 over 4. That is x to the power of 5 over 4. And here we have dx, right? So to find the net change, again, just we need to evaluate this definite integral. So that is equal to, here we have x to the power of 4 over 3. Let me write it as a fraction here. 4 over 3 plus 1 over 4 over 3 plus 1 plus x to the power of 5 over 4 plus 1 over 5 over 4 plus 1. And it is changing from 0 to 1, right? As see here, when it is 0, that's equal to 0. When it is 1, the first part, right, it is 4 over 3 plus 1, that is 3, right? It is 3 over 7. And how about this one? It is 4 over 9. So which is equal to 6 to 3. 3 times 9, it is 27. 4 times 7, 28. is equal to 55 over 63. Example 5, let C of X be the cost of producing X units of a certain commodity. Then the net change in the cost of this production, right, will be, what is it, from x1 to x2, C prime of X dx. Let's equal to C of x2 minus C of x1, okay? And also for the position function, okay, let's just have a look at examples we will do in the class, all right? The last example, let me just show one example, and I would like to finish our today's class. And the figure below shows the graph of the function f of x equals sine of x between x equals 0 and x equals 2 pi. And compute the definite integral of f x over the interval from 0 to 2 pi, and the area between the graph of f of x and the x-axis over 2 pi, right? The solution, part A. If you find the definite integral over this, that is from, what is it, 0 to 2 pi, our function is sine of x and dx. So that's equal to the one of the antiderivatives of sine of x is minus cosine of x from 0 to 2 pi. So that's equal to one, actually cosine of 2 pi, it is 0, 1, cosine of 0, it is 1. So this integral is equal to 0. And how about the area between the graph of f of x and the x-axis? As I say here, from 0 to pi, it is positive. From pi to 2 pi, it is negative, right? To find the area, I have to multiply this negative part by minus. And that's why to find the area, I have to evaluate this from 0 to pi, because at pi, this change is the sign. Here we have sine of x and dx plus, and here we have, what is it? Absolute value of, what is it, integral from 0 to pi and sine of x dx. Actually, this one is from pi to 2 pi, because over this interval, it is negative, right? Because it's asking the area, not the integral itself. So simply, I have to just find one of them, right? Because they are symmetric, and multiply by 2. So multiply by 2, and this one is, again, minus cosine of x from 0 to pi, right? So cosine of x, here we have minus 2. Cosine of pi, that's equal to negative 1, minus cosine of 0, that's equal to, again, 1. So the answer is, it is 4. So what do we understand from here? We find the area between the graph of y equals f of x and the x-axis over the interval AB. So we have to subdivide AB at the zeros of f and integrate f over each subinterval and add the absolute values of the integrals, because area cannot be negative number, right? Again, about this question, we will do in the class. Okay, guys, have a good day. See you tomorrow. Okay, thank you. Bye-bye.